So one thing one might ask oneself is, how was this missed empirically? Why was it that, Faraday discovered Faraday's law by, shoving magnets into coils and watching things? Why did this require some theoretical addition? Why wasn't this seen empirically? Well, so think about that. Let's just do, kind of a back of the envelope scaling argument here. Let's suppose, let's just look at the scales. So y was the displacement current not deduced through experiment. Well, let's just do a scaling argument. Let's say it's the characteristic scale of length associated with my distribution and time associated with the time scale over which the charges are changing, things are changing in time. And let's just do there's this derivative is whatever the characteristic max strength of the magnetic field is over L goes like whatever the current is over C plus 1 over C times the characteristic times D. I mean, there's some, that's just like the high school physics version of this equation. So the question really is, what is the relative contribution of the conduction current to the magnetic field compared to the displacement current contribution? Well, what E are we talking about? Well, the E here that we're talking about, if it's, if E is proportional to rho, then that's kind of the same thing as this, right? That's the electrostatic contribution. But if E is coming from Faraday's law, then that E itself is proportional to, well, E over L is proportional to 1 over C T D, which says E, that E goes like L over C T B. So if we put all that together, what we see is that B over L goes like whatever the conduction current contribution is plus C. So what we see here is that this term is only of order this term. So the displacement current contribution only when L is on the order of CT. Or, said another way, when L over T is on the order of the speed of light. So what this says is that if I have a circuit or a charge distribution in which I have changing currents, you know, I have RF or microwave or something like that, the contribution of the displacement current to the calculation of what the magnetic field's in is that circuit is going to be tiny unless my charges are moving at relativistic speeds. And that's why we often have the situation where we have quasi-statics, where we have, if you think about a, you know, an RF circuit or something you have in the lab, you calculate these things based on, you know, these inductance principles, ignoring the displacement current. You just treat it as though the magnetic field is just related to the conduction current, ignoring the displacement current. So the only time, if I have this localized circuit where I have to worry about that, so the quasi-statics is to say ignore interplay of the dBt and the eBt. I can ignore that if I'm moving at relativistic, if I'm moving at non-relativistic speeds. Now that's not exactly true, as we know, because it's not, even if t is long, that is to say, even if this speed is small compared to the speed of light, I might have, so there's another condition where we can satisfy L on the order of CT for non-relativistic speeds far from the distribution. In other words, here's the distribution. Things are moving around here. But here's L equal to CT. As long as I'm looking very, very far away from the distribution, I can have this be true. And this is called electromagnetic radiation. So of course we know that the addition of the displacement current to Maxwell equations allows for electromagnetic radiation. And if I have change in currents, the circuit will radiate. Now, it might radiate at very, very, very long wavelengths, which means I need to look extremely far away from the circuit to see that radiation. And as we'll discuss, the amount of power that's actually radiated can be tiny. But nonetheless, there will be some radiation. Whenever I have accelerating charges, they radiate. The amount of radiation might be small, but it is. Nonetheless, if I ignore the so-called retardation effects, that's to say, I ignore the retarded time, the time it takes for light to propagate to where I am, because I'm looking so close, and light basically propagates instantaneously across the sample, then I'm in the quasi-static regime. And most of electronics that we do is done in quasi-statics, unless we're talking about antennas or something like that, where we're talking about the actual radiation. Okay? Is that clear? Very important concept. All right. So now that we have Maxwell equations, we can start cranking on a number of things. And one of the first things I want to talk about is the idea of conservation laws in electromagnetism. So we've already visited one example of conservation law, the conservation of charge. But I want to talk about this in a more generic way. It's not just about electromagnetism, but we'll apply these ideas in the electromagnetic context. So what does a conservation law say? It says if I have stuff, like charge, or whatever that stuff is, energy, momentum, mass, ideas, maybe they're not conserved, but that's okay, we can take that into account. We want to know what is the rate of change of this stuff, total amount of stuff. Well, we can think about this stuff, we can define a few quantities. First thing I'll define is rho sub q is the density of stuff. That is the amount of stuff per unit volume. And the flux density, which I'll call J sub q. This is the rate of flow of stuff per unit area in some direction. And then finally, I'm going to define R sub q is equal to the rate at which stuff is created. This will be generally a function of position and time. So will these other quantities, but I just didn't explicitly write it there. Rate at which stuff is created at the space-time point xt. Then I can write down a generic form of a conservation law. So the rate at which the stuff changes is equal to, well, it'll change if it flows. So here's a picture. We have some stuff. Here it is. And, you know, it could be moving around, however it moves. And, you know, have a little magic wand and poof, stuff is created or destroyed. Or, you know, I can ask now, how much stuff is there inside this volume? It changes, well, it decreases if the stuff is flowing out of the volume. So I'll make n have the normal out of it. So I look at the flux of this stuff through that. And it can increase if it's created. So there's some volume integral. This is the surface that bounds the volume. And this is the general form of a conservation law. Okay? Now, for the case of charge, this was 0, because there was no rate of creation of charge. But if we're talking about something like electromagnetic energy, well, then it can be created. Of course, it comes from mechanical energy or some other source. But if we just concentrate on the electromagnetic energy, it can be created or destroyed and transferred between the fields and the charges. So let's, first of all, write this equation in a, this is the global form, so to speak. Within this volume, we want to look at the local form. So we write this as the rate of change of the density of stuff And if the volume is fixed, then that's equal to the partial of that. Moreover, this is equal to the volume integral of the divergence according to Gauss's law. And since this is true for an arbitrary volume, we have now a local relationship which says d rho dt changes because there is diverging or converging flow, or the stuff is just locally created or destroyed. And this is the general form of the continuity equation. Okay? So let's look at this for the specific case of electromagnetic energy. So let's look at conservation of energy in the field. So that's our stuff. Yeah.
Just really quick, what would happen? So if you had a volume that was moving with time, like how would you express the time derivative on the left side?
You would have to, as we did in the context of when we're thinking about the moving loop, we need to think about terms that look like v dot the derivative, right? If I had some kind of, if I wanted to look at the time derivative of a function that's a function of time, then this is the partial, if it's also an explicit function of time, plus v dot grad f, for example. So then I'd have to think about how these terms affected that. It's not a simple problem. I have to think pretty carefully about the specific context. But I'd have to think about this flow, right? Because the thing is moving.
Yeah. Okay.
It's really not particularly important for the derivation at hand because one would, if one wanted to calculate the global quantity, one would fix the volume.
Yeah.
But you're right, if it was moving, we'd have to be much more careful about how we'd have to think about how the volume elements swept out as we move through space.
Yeah. Just curious.
But there's no simple expression. I would say. Okay, so we're talking about conservation of energy in the field. So stuff equals electromagnetic energy. So the rho sub q goes to the energy density in the field, which we typically call little u. And you remember that's 1 over 8 pi E dot E plus 1 over 8 pi E dot D. Isn't that nice and symmetric? Love that. So this is the energy density in E and D. And I need more chalk. So let's look at how the local energy density in the field changes with respect to time. So that's equal to 1 over 4 pi E dot d E dt plus d dot d dt. Just taking the derivative, brushing the chocolate down the foot. All right? So now we know what these things are from Maxwell's equations. So the E dt is equal to C the curl of B minus 4 pi J from Ampere's law with the displacement current. Right? And the BBP is equal to minus C, the curl of E. So what we got here is that this is equal to 1 over, or C over 4 pi, E dot the curl of E minus B dot the curl of E minus J dot E. And that's equal to this. Now, what is this? J dot E. You remember we discussed when we talked at the beginning last week about the whole idea of only heating, that J dot E was the rate at which J dot E equal to the rate at which fields do work on charges per unit volume. Right? That's what we call only heating. However, minus J dot E thus is equal to the rate at which charges do, not do, but do, work on fields per unit volume. So minus J dot E is equal to the rate of creation of electromagnetic energy per unit volume. Now, minus J dot E is negative, well then we're not creating energy, we're dissipating energy. But if minus J dot E is positive, then we're creating energy in the electric and magnetic fields. What about this other term? Well, we kind of recognize that, maybe. Looks like a product law. Let's do a little aside over here. World famous aside. Del dot B cross B equals Y. How am I going to do that? I'm on the desert island. No Siri to help me. What do I do? Write it out in the components, right? Gotta know my tensor notation. So this is I times E cross B I, right? But E cross BI is epsilon I j k, elemental P, no, E j B k, right? Epsilon I j k is a constant, goes through the derivative, and I get bk partial I ej plus bj partial I bk. All right? So now, what is this? Well, this is equal to, if I put that on the other side here, this is del cross E dotted into B. That's the first term, right? Because epsilon I j k partial I E j is del cross E, and then I sum over k by that. Okay? And then I get this one. So now I have to switch the I and the k, that's a negative sign in the non-cyclic permutation. So it's minus del cross B dotted into B. So, what do we have here? It says here, thus, that the rate of change of electromagnetic energy in both the electric and magnetic field is equal to, have the negative of this, have minus del dot C over 4 pi E cross B. Minus J dot E. And this quantity is known as S, is known as the Poynting vector. Now, Poynting was a person with a Y. He has a very fortuitous name because something is pointing somewhere. But he's a vector. And this is the Poynting vector. Everyone remembers the Poynting vector, right? So we have constant. So enthusiastic. Chalk stands not a chance. Conservation of energy is known in electromagnetism as Poynting's theorem. And Poynting's theorem says that the rate of change of the total electromagnetic energy is equal to minus the divergence of the Poynting vector minus J dot E. Where U is 1 over 8 pi E squared plus B squared. The Poynting vector is C over 4 pi E cross B. Or 1 over mu naught if you're so inclined. Okay? This is the equation that describes the local creation, destruction, or flow of electromagnetic energy. And Poynting's vector, first of all, what are the units of the Poynting vector? Well, the Poynting vector is the flux of stuff, the flux density. So the stuff here is energy, and it's the rate of flow of stuff per unit area, right? So the units of the Poynting vector are energy per unit time per unit area. Okay? Which is power per unit area. The units make sense here because we know that E squared or B squared is an energy density, energy per unit volume. So if I multiply that by C, well then I get a flux. Just like when we multiply charge density by the velocity of the flow of charge, we got the current density, the flux density of charge. So it's always the case that the density times the velocity is the flux density. All right. Very good. So what this says, of course, is that if I were to integrate the Poynting vector through a closed surface, this is equal to the flux of electromagnetic energy out of the surface. All right, so I'm going to remind myself where I am. These notes. Here we are. So let's look at the flux of the Poynting vector through a closed surface which is at, oh, I'm sorry, let me redraw this. So here we are, here's the resistor. Here's the particular radius we're drawing. This is my imagined volume, which has radius r. And I want to know what is the flux of S dot dA out of this volume. Okay? So you see that volume is just a little cylinder inscribed in the big cylinder. S has no flux through the top and bottom of the cylinder. It only has flux through the sides of that cylinder. In fact, it's negative. And what is that flux value? Well, it's what we have here. We need to find out what is, so S is equal to 4 pi over C E cross V. So S, magnitude of S, or S itself, is equal to C 4 pi magnitude of E, the magnitude of B at that radius in the minus rho hat direction. The electric field is constant inside because it's proportional to J, and J is constant inside the resistor. So what we have then is what? The flux integral is going to be equal to S going into this volume, which is S only on the sides, and this is S at R times the area of the label, which is the perimeter of the label, times the height of this resistor. Okay? So what does that equal? That equals C over 4 pi, the negative sign, the magnitude of B. The magnitude of B is given there. It's equal to 2 pi r J, which is constant. Actually, J is not a function of R in this problem. It's uniform. Over C times 2 pi r times the height of that resistor. Okay, let's see if we got it right. We get the 4's cancel, one of the pi's cancel. I have equal to minus the c's cancel, pi r squared j e.
H to your right.
Times h, yes, thank you. Important. Okay, which is equal to the volume of the cylinder J dot E. So what we find in this case is, as expected, the flux of electromagnetic energy is what we said it should be. It's equal to how much energy is being dissipated. This is ohmic heating. The resistance in the circuit is dissipating all of the electromagnetic energy that's flowing. So energy conservation rules the world again. Yes?
How does that how does that fit in with the whole like Drude model picture of
I don't know, home heating and like.
Well, I
electrons
mean, the
heating
Drude
up and
model,
heating
of
things.
course, is a specific example of where the energy goes.
Okay.
But the Poynting theorem is completely generic. It doesn't say anything about the relationship between J and E. The relationship between J and E that we wrote down, the Ohm's law, comes from a Drude model, but in fact we never used this. You notice sigma never appeared anywhere here.
Okay.
Now, one thing you may note in this, is you say, what the? I mean, this is a standard, undergraduate problem that I just did. You may have seen it already. If you recall, go back, I'm sure you did it in your undergraduate classes. But one thing you probably never did is the following. I mean, give me a break. You're telling me I got current flowing through this resistor and the energy is flowing radially into the circuit? That's the flow of electromagnetic energy? I mean, power is flowing in the circuit here. Power should be flowing